The time is officially 3 o'clock. Right? So, we're missing my kind of stuff. Right. We'll do a slow start then until we're all of us are here. Right. So I read a paper. I read a paper about well, the paper is called Neural Ordinary Differential Equations. It's not a neuralization paper in the sense that we're not taking a traditional thing and putting a neural network on it to solve something. So in that sense, this title is a bit misleading. There are many other things also in this paper that are misleading. So I'll try to steer out of those, try to clarify things. But the paper and the idea is really cool. So I hope to be able to convey that. Right. I'll start with my introductory slides about neural networks, as I always do. And this time I kind of painted this neural network with equal sized layers. We have here an input layer, we have one or more hidden layers, and we have an output layer. That's a basic neural network. We do some simple computation at every layer, such as multiplying with a weight matrix, adding some bias vector, and squashing through some nonlinearity, such as sigmoid. Right. So what happens when we're making these deeper? Well, not much happens. We're adding more layers. We still have the same input. We still want the network to output the same output. But we're doing this in more steps. We're doing more steps, and we're doing less of a transformation in each step. So each step is a transformation from an input vector to an output vector. In this special case, we're having all vectors the same size, which simplifies things later. So we're doing smaller and smaller steps when we're increasing the network depth. This reached some kind of culmination in late 2015 when residual networks were proposed, and they looked something like this. We have super many layers because we were able to train a network with super many layers. And the reason for being able to train this network with such depth is these residual connections. The residual connections is just that we're feeding the input not only to the layer, but also to after the layer. So after a layer, which we here call F, we're adding the output from F to also the input. Just adding them, making a vector sum. So that means that the state at time t plus 1 is equal to the state at time t plus the transformation made by F. That means that F is starting to learn a difference between the input vector and the output vector, instead of learning the transformation from the input to the output. All right. So we're learning a difference now. This difference, of course, becomes smaller and smaller if we're increasing the depth. Or the network learns something with more capacity. Both are probably true, but it's still interesting to see what happens when we're really shrinking this step that we're doing at each layer. Right. But in the limit, F becomes just the direction where we're going. We're taking now an infinitesimal step. Instead of having a layer doing a large transformation, we're taking a small step in some direction. And F can now learn what direction is this. And this is where this paper comes in. So So they propose something that they call the ODE net. It is a neural network architecture in a sense. It has continuous depth in a sense, and we'll see the details on why it is like this. We're now formalizing, or we're now formulating what we're learning, the model with this vector Z. Z is now the state of the network. In the paper, this is a bit confusing because in the first couple of pages they call it age. They don't change this when going from one model to the other. They just change it. Now it's called Z. So Z at time t is the state at time t, or depth t. So when propagating through the network, we're going from t equals 0 to t equals capital T. And that's how we're transforming Z from time 0 to time t. That's also why we formulate it or write it as Z is now a function of the time parameter. Right. So now we're going from parameterizing layers to parameterizing the derivative, the gradient with regards to t. So at each position, each time, we're just learning to know in what direction should we move to get the next state Z. Right, and this, of course, defines this nice vector field. On the left-hand side, we have corresponding view of the residual network where we have discrete layers. So here, in this case, we have 5 layers. We do some transformation at each layer. We end up in a new point. We get to the next layer. We end up in a new point, and so on. On the right-hand side, we have the corresponding view of the ODE network, where we have these trajectories through this vector space, which is defined by the gradient of the state, not the gradient of the parameters, but of the state, as t is increasing from 0 to 5. We'll also get into the details on where the dots in along this trajectory will end up, because that's kind of where this is continuous and where it's arbitrary. Okay, so to be able to use this vector field as defined by these gradients, it's not very clear, but this is also a vector field. Just a bit right on this screen. So to be able to use this, we're using a black box solver for ordinary differential equations. These are differential equations that are defined just by this derivative that we talked about. The derivative with regards to the parameter t, which is the time or the position in the propagation through the network. It goes from 0 to capital T. And here we're calling capital T T1 as well. Part of all the confusion in this paper. So we have the vector Z. We want to know what is Z at time capital T. We do know what Z is at time 0. And we do know what is the derivative at each time, because this is parameterized, it's apparent. So we just integrate this, right? We integrate the derivative and we get the function. No problem. We can use the Euler's method for this, and this nice illustration shows that, well, you could end up a bit off, but you still have some kind of approximation. So, for example, Harrer et al. 1987 proposes more sophisticated methods for solving these ordinary differential equations, where you can have error guarantees, and which adapt the evaluation points of the function dynamically. while evaluating the function. We start out with Z0, and Euler takes these fixed step sizes, and an adaptive solver instead takes as many evaluations of the function that is needed or required to get some certain level of precision. I think that this image is from the authors. I don't know how they created it because the previous image where we have the exact trajectory, the true solution, it looks suspiciously similar to the one from the adaptive solver. And I suppose it should be straight lines, or perhaps not. And a solver could actually make use of second-order derivatives to have the curve of the line. Anyhow, this is kind of the core of the architecture of the ODE net. This is how we define the network. So the network is stepping through this vector field, using this vector field to step through the space of internal representations. And then these evaluations are done dynamically. And you can see in this picture that it makes more evaluations of the function out with larger values because I suppose the vector field changes more there. And in the middle, it's more clear, and the solver can take larger steps. So this is just one of the dimensions. And when you start with the value 0, you end up very close to 0. When you start here, you follow the directions as defined by the vector field, and you end up somewhere in T equals capital T. So, how can we train this? We all know backprop, we all know how to train a neural network that has fixed number of layers, but what about this? Well, I'm not actually going to go into detail about this, but in the paper they define this other ordinary differential equation, and they show that this is some kind of a continuous time limit of doing standard backpropagation. It's called called the adjoint sensitivity method, obviously, on the slide. And they define this adjoint as the derivative of the loss. It's a standard loss, time equals capital T, with regards to Z at this at time T. And then we find the derivative of this adjoint, AT, and then we find the derivative of the loss with regards to theta using the adjoint and the derivative of f of Z. Right. And in practice, it's also solved by this ODE solver. Well, one of the niceties is that you don't have to save all the states. It can then be made in constant memory size, but they do this with re-evaluating the original function f during the backprop stage. So I'm not sure how much of a win this is. Right. So the first experiment in this paper is surprise, surprise, MNIST, handwritten digits, and they show that they get the same performance as a residual network with much fewer parameters. So we're having a small ResNet, actually not sure how many layers, a small one with 0.60 million parameters, and we have 0.22 million parameters in this ODE net, and get a similar performance, which is pretty cool. So one of the reasons that you can save parameters here is that you share parameters over all the function calls. So in each layer of a residual net or a standard neural network, you have a specific set of parameters for each layer. Now we're starting to share these. So in that sense, it's more similar to a recurrent neural network, where you have these shared weights. But in addition, you can also query at an arbitrary number of times. In practice, they see that the solver makes 2 to 4 times as many calls to F as there are layers in a corresponding residual network. I suppose they are comparing a network with a similar performance here. Also, during training, the number of calls to F is increasing quite a bit, I suppose. They motivate this by the fact that when you train, the dynamics get more complicated, and you need more evaluations of the function to actually know how to traverse this space of representations or state space. They also see that NFE here is the number of function evaluations, and the number of function evaluation during the backdrop stage is about half the number of the forward stage. The colors in this plot are corresponding to the tolerance given to the ODE solver. That means that we're at purple here, we're giving it the tolerance of n to minus 5. So it has a smaller tolerance, which means it evaluates the function with a higher precision, which means that it makes more calls to F. In essence, that means that we're having a deeper net. Right? With the tolerance, they show that they can change the speed. They can make a trade-off between speed and accuracy. So with this higher accuracy, they also make more calls to the function. That's, I guess, fairly obvious. Right. So the second experiment in the paper is what they call continuous time models. Here they are modeling a sequence of data points, and they do this fairly limited experiment with synthetic data of points in two-dimensional space that are drawing some kind of a shape. And well, they do show that they can have irregular time intervals. They do get nice results, but they also blend in an RNN. So they're kind of training a sequence-to-sequence model with the encoder being an RNN. That means that the encoder is seeing the observed data points here. It gets its internal representation with normal training, and we get the mu and the sigma as a variational autoencoder, and the decoder is this ODE net that that traverses the state space, samples from it, and makes its predictions, which is then to copy this shape that was drawn. It's spiral. They draw spirals. They do show in the results that the extrapolations are pretty nice, and that the learned trajectories are smooth and nice. And it's with this slide that there was some error with the importing from the original authors here. So the ground truth is green here. The observed values are green because they add some Gaussian noise to them. And the prediction is blue when we are copying, and red when we are making this extrapolation, things the network hasn't seen. And well, the latent ODE on the right, it makes a nice smooth spiral, and the RNN on the left makes a not so smooth spiral. And I guess that says something. And actually here in this experiment is where they are a bit more clear about what we are doing, because I haven't yet mentioned F. I have mentioned F many times, but I haven't said what F is. F is a neural network, and that's as much as they say in the experiments of the ResNet. I can just speculate that perhaps in the ResNet experiments, the F is some module that is similar to the ResNet module without the residual connection, because that makes no sense. In the RNN case, they actually specify what F is, and it is a small feed-forward neural network with one hidden layer and 20 hidden units. And the internal space, the latent space, is 4-dimensional. Right. The third and last experiment that they do is about normalizing flows. Normalizing flows is something proposed by Kabak and Van den Eenden in 2010, where you take a transformation from one random variable to another, and you learn this transformation in a number of steps, and you're able to model posterior distributions that aren't necessarily within the normal classes that we usually enforce. So it doesn't have to be a Gaussian or a mixture of Gaussian or things like that. The limitation is that you kind of have to compute the determinant, which is expensive, which means that these models are made deep instead of wide to make them easier to compute. The nice thing is that they produce a valid probability distribution, and already the output without any normalization is a valid probability distribution. Now, in a surprising thing that they show with an actual proof in the paper is that when you take continuous infinitesimal steps and the space is continuous, you don't have to compute the determinant anymore, and it suffices to have the trace operation, which is obviously much cheaper and linear to compute. And they show that they can train this with maximum likelihood to output distributions that are this looks pretty cool. So I guess the visualization here shows that you input something that is Gaussian, and then you have this flow defined by a similar vector field as in the previous slides, and we end up getting this this new distribution, which is already normalized and nice. So there are a couple of requirements here. So it has to be invertible with the transformation, and it is in this case, and everything turns out nicely. Okay, so they show that this can be used as a generative model, and here are some results from the experimental evaluation. So here is the target distribution. These are the previous normal fields, which are not continuous, and the last three columns here are the continuous normal fields. And I guess with m is here the width, k is the depth, because in the normal fields case we have width 1 each layer. And I suppose you can say that the continuous normal field learns quicker and perhaps sometimes even more accurately, even when the model has been scaled to suitable size. Although at the 32 case, I guess both work fairly well. So with this, with the continuous normal fields experiments, they also show pictures which I apparently don't have in my slides, where they kind of train the model to output images and the inner structure of a maple leaf, and it also looks very nice and convincing for the eye. So, concluding remarks. This is a memory efficient approach because we don't need all the parameters. So the parameters don't scale with the number of layers. There is not really the notion of layer here. We have the function f that finds the vector field. It has parameters. They show that they can use fewer parameters here than you do in a ResNet. With this tolerance parameter to the ODE solver, you can trade off accuracy versus running time. They have experiments with irregular observation times. I guess one of the things you could complain about is that these experiments are fairly limited and they're made with synthetic data, and we don't really know how this could be used with real data or real problems. It looks fairly promising, I would say anyway. They show the continuous normalizing flows, which obviously has its benefits. On the downside, we don't have guarantees on the computation time, and in general, we have more calls to the F function than we have layer applications in corresponding REST. All right. So, no questions. Come on.
Some of the questions in the beginning of the talk, they remind somehow dynamic programming. You have some goal and computing everything. How you can reach. Is it correct observation?
I guess dynamic programming is generally a way of formulating things so that you can make recursive calls. I'm not sure. Not doing recursion here. I guess some of it could be formulated that way, but we're more doing like forward passes, and even the backward pass is solved via this ODE solver. You just find the function that you will integrate over, but in the other direction. So you're integrating from time to the step.
So I have a question. Can you hear me?
Yes.
So it's a fairly sort of superficial question, but in the comparison or in the sort of suggestive comparison visually between ResNet and ODNet, they suggested a sort of a continuous transformation in ResNet that was then sort of you achieved as well in the ODNet. And was there any kind of analysis of the transformations in ResNets that would support this visualization?
It's you do take the step from like you start out with a regular ResNet, and as you go into shorter and shorter step sizes, you do end up with this formulation that you can interpret the f as the derivative.
You're saying that mathematically, you sort of this is the limit of the ResNet layer. Yes, yeah. but empirically, when training ResNets, what types of transformations do you in fact achieve? I'm just curious if there was an analysis of this.
Okay, that is, I guess, a good question, which they don't have an answer.
Okay.
I guess it is. I guess it is under the assumption that you want the same output from a layer as you do without the residual connection. You would then conclude that you need to learn the difference rather than the transform from input to an output. And with this assumption that you are learning this difference, which is probably, at least to some degree, true, you do in the limit end up with this vector field. And it goes the other way around, that the ResNet is an Euler expansion of this vector field.
And another question relating to sort of just the conceptual understanding. If when ResNets, I don't even remember the exact architecture, but I mean, ResNets are typically used for image recognition, computer vision type, so convolutional neural networks, and they will not have the same dimension over the transformations, etc., etc. So I can't really visualize what this transformation means in those terms. Can you help my understanding?
Yes, that is a good point, and I guess that's why they refer to exactly ResNets also, because this adding of the residual connection requires that you have the same dimensionality with the previous state and the next state, and that is true in large portions of a ResNet model. Then you're completely right, and they do use pooling and downsampling in the model, and this isn't applicable. You cannot really do that here. You could replace every such block that you have in a ResNet with an ODE-net, but I suppose when going from one resolution to the next, you have to do something to work. So either define a new ODE-net for the next section of it, or something even more clever. They do use this as a neural network module. So they show that in the image classification problem, they do feed it through a fully connected layer in the end, and they have 10 outputs of the internal state size, which they haven't specified. They do publish the code, and they say also that they have since ported it to PyTorch. I'm not sure. Perhaps it is in a useful shape. In the first I heard about this, it sounded like they're using lots of different things from lots of different places. So in practice, it's a real big hassle to make all of it work at the same time. But they have released code, and I guess we could check it out. I do think it's a fairly interesting direction. I think it could be really cool. I also think it's one of the really cool things is that while you are sharing parameters between every call of f, because you have the same parameters at every time, you are telling it the t parameter, so it has the signal of where in the network you are, and you can do different transformations in different depth. But it's also the case that when the change between t is small, the transformation will also be very similar. And I think that could be easy in the transformations that people can follow. More questions?
No, we're happy here.
Happy. That was good.
Okay.
Hey.
Thanks a lot then.
Thank you.